So, does anyone have any homework 2 questions?
No, but I've got homework 3 questions.
We're not going there. Maybe Monday. Well, yeah, definitely on Monday, but nobody?
I have a question, number 15.
Okay.
I'm not sure how extend do I need to do that?
Oh, okay. Yeah. 15 is a long problem, as stated. And actually, I was.
You mean we have to do all the.
Well, let me think about this because I just looked at Vivian's solution. Yeah, she had done everything.
Okay.
Now, I will say that because if you try to show that you have a set of functions involving sines, cosines, and one constant function, so that leads to several possibilities. There's also, like, for cosines, like if looking at n equals k or n not equal k, so it can get a bit repetitive. So okay. So to cover, to try to cut out some of the duplication,
Yeah.
I will say that focus on showing that if you have the cosines and constant function, that those are orthonormal, and also show those functions are orthogonal to the sines. So that cuts out some possibilities, and then that way there isn't duplication of work. Because I don't want you guys like writing something, then you pretty much write almost the exact same thing again. I mean, it gets silly after a while. Sorry, Vivian, for being a guinea pig on that. Who'll be watching this? But yeah, I wasn't thinking about that when I picked this problem out. I thought, oh, this is something that you guys could definitely do. I wasn't thinking about how long it would take to do. So sorry about that. So I mean, if I put that problem on a test, it'd be the whole test. So I'm not going to do that. Okay, so that's the other thing. Establish a proof of theorem 1.4. So that is okay. So in that case, you're trying to show the coefficients work out a certain way. So again, just focus on the constant function and the cosines, and don't bother with the sines because that works out exactly the same way as the cosines. It's not interesting. so that'll save some, not a whole lot, but okay. So well, sorry to those who've already turned it in, but yeah. Okay. Oh, actually, I just realized I misread my email because, yeah, you're the only one who's turned it in, and another is finished but about to turn it in. So, okay. I just realized, yeah, I have revisions of homework 1 I still need to get to, so I will try to get to those soon. Other homework 2 questions? Okay. Haven't got to it yet? Okay. Oh, okay.
No, it's enough to say this. Like I just realized it. In the Fourier Series expansion, we have A naught plus the summation of.
Yeah.
Yeah. In other books, they do A naught over 2. Then in that case, A naught, the formula for A naught is just 1 over L.
Yeah, it's choosing a certain convention because that way, a lot of authors like to do a naught over 2 because then the constant in front of the formulas is the same.
Yeah.
And actually, I kind of prefer that convention, but for sake of the homework, I don't really care as long as you define what you're using. So, yeah. Anything else? Oh, okay. So I get through these 3 pages and we all go home. Well, actually, I don't go home after this, but I'm done. Okay, we leave this room.
We leave this room. Oh, go back to your office and meet with students.
Yes, that's exactly what happens.
Well, that'll make 2 of us.
Yeah, but that's pretty much the story of every day. Well, fine of me. Beats committee work.
Oh yes, I can definitely. I haven't been on any committees like yours, but I can definitely imagine that is true. Ugh.
Okay. Yeah, that's the problem with faculty. They love to talk. Okay. So we're actually starting a new chapter today. Chapter 2. Feel the progress. So we've been dealing with Fourier Series all this time. But now we're dealing with the Fourier Transform. And I'll emphasize this is the continuous Fourier Transform. So in Fourier Series, you have cosines and sines, and or complex exponentials, and you say cosine sine different frequencies, like cosine kx, sine kx, where k comes from a discrete set. So it's the integers on minus pi to pi, or integer multiple of something on a different interval. Here, this is different, where the frequency variable is from a continuous domain, so the entire real line, and we're dealing with functions f of x defined on the entire real line. And so what I'm going to do is I'm going to informally derive the continuous Fourier transform from the discrete-based Fourier series. Okay, so, and it'll just be so much easier to do that using the complex form, because then we don't have 2 types of terms. Okay, so we're working on the interval minus L to L, because we're going to take this generic interval and we'll extend it to the entire real line. So n going from minus infinity to infinity, alpha n e to the I n. Oh, dang it. Okay, already a typo in the notes. I have a T where I should have an X. Okay. And I n pi x over L. Okay. And then we have the usual definition of the complex Fourier coefficients. So 1 over 2L, integral minus L to L. And here I do want a T, f of t, e to the I n pi t over L dt. Okay. So now what I'll do is substitute this into here. So what I get then is, like the other thing I'm going to do is I'm going to take the limit as L goes to infinity. So on the entire real number line, f of x will be the limit as L goes to infinity of this Fourier series with the alpha n substituted in. So I'm going to have a sum. Okay, and I'll have 1 over 2L, integral minus L to L, and then I'll have f of t. And what I'm going to do is, I have this exponential inside the integral, and I have this other one that's outside. I'm going to take this one that's outside and move it inside, and that should be a minus right here, the definition of a complex Fourier coefficients. So now you have e to the minus I n pi. Okay. Well, what I'll do now is no minus x minus t over L dt. Okay. So I had e to the minus I n pi t before. That minus is still there. But this one without the minus gets moved inside. So that's why there's not a minus there. Okay. Now, for convenience, and define some things here, I'm going to find lambda n to be this quantity that we see throughout n pi over L. So that'll help condense things a bit. And I'm also going to define delta lambda. So a change in lambda is going to be lambda n plus 1 minus lambda n. So that's just going to be pi over L. All right, so now when I make these substitutions here, then okay, so now I'm going to have the same sum. So then, if I go ahead and just put in a delta lambda out here on the end, well, delta lambda is pi over L. Okay, something seems weird here, but okay. Oh, all right. So here I'm putting pi over L. That means back in here I got to put L over pi. L over pi will cancel with the L and put a pi down below. So now I have 1 over 2 pi. So in other words, 1 over 2L is the same as 1 over 2 pi delta lambda. Now, it'll become clear in a moment why I'm doing that, because it seems kind of silly. Okay, and then integral minus L to L, f of t, e to the I lambda n, x minus t dt. Okay. All right. Now, that whole, everything that's in the summation, I'm going to label this as a function f sub L evaluated at lambda n. So we have some integral with respect to t over interval minus L to L, and lambda n is a parameter that I'm going to identify here. So I'm thinking of that whole integral with 1 over 2 pi as a function of lambda n. But it also has this parameter L indicating what interval we're integrating over. Okay. Now, why on earth would I do that? Because I can now say that this is the limits of goes to infinity of a sum FL of lambda n delta lambda. Okay. All right. Okay. Now, so the thing is, delta lambda is pi over L. That means as L is going to infinity, delta lambda is going to 0. This is a Riemann sum. Okay, so what we end up getting is all right. So So what we get now is getting the limits as L goes to infinity of the integral from minus infinity to infinity of FL of lambda d lambda. All right. For some reason, I know I just read this right off my notes, but something feels a little off. So I want to make sure about this. Okay. Well, at least it agrees with what's in the book. Okay. Honestly, okay. Integral 4 over 2 pi. Okay, minus infinity to infinity. E to the I lambda. Okay. Yeah. So, is it raining? Yeah. Oh, okay. Well, good thing I brought my umbrella. This morning is like, oh, totally sunny day. Okay. So, even though I'm going with what's in the book, but I'm actually also simultaneously objecting to what's in the book for this reason. This delta lambda does not really become a d lambda until you actually take the limit as L goes to infinity. But if that's the case, then we have a d lambda here. Why is this limit still here? Now, what I could see instead, maybe, is if we're working on the interval minus L to L, because we really have two limits at once going, because this series, by definition, is a limit as little n goes to infinity. Then we also have a limit as L goes to infinity. So now, the end result of this, when I actually take the limit as L goes to infinity, turns out to be what we want. I think the presentation from a book about how we get there is maybe glossing over some things. But yes, it does make sense that delta lambda is going to 0. So we have this effect of a Riemann sum becoming an integral. It's just, yeah, I'm presenting this under protest. It's just that right now I don't have the energy to fix it in the most rigorous way. And it's really the end result is what we actually need here. Because then what I can do is, if I go ahead and substitute this definition of FL of lambda into here, so yes, my board use is a little interesting, but I also have to keep in mind what's showing up on the screen. So f of x is now 1 over 2 pi double integral minus infinity to infinity of f of t e to the I lambda x minus t dt d lambda. But then what I'd like to do is separate this a little bit, because here I have both x and t, but I can take e to the I lambda x, and I can pull it out of the inner integral. It just has to stay within the outer integral. And for symmetry, I have this 1 over 2 pi that I can break up into 1 over square root of 2 pi, 1 over square root of 2 pi. So, and the problem is, although I'm not out of board space, I am out of screen space. So, all right. So what I'm going to do now is, all right, I'll erase the old stuff, which is what makes sense anyway. And if I have time, which I'm not likely to, I would like to revisit the original presentation and describe these limits more properly. But I can tell you that it's not something that's going to affect your homework problems. So it's not, or the exam, so it's not really something that has urgency. Okay, so now I can say f of x is, so I'm going to have 1 over square root of 2 pi outside of everything, integral minus infinity to infinity, and then 1 over square root of 2 pi, the other integral minus infinity to infinity, and then I'll have f of t, e to the minus I lambda t dt, and then I can put parentheses around all of that, and then I have e to the I lambda x without a minus d lambda. Okay. So now, what I put in parentheses, I'm going to call this f hat of lambda. So now what we have is f of x is 1 over square root of 2 pi, integral minus infinity to infinity, f hat of lambda, e to the I lambda x d lambda, and f hat of lambda has a very similar appearance. 1 over square root of 2 pi up front, integral minus infinity to infinity. But now we have f of t, e to the minus I lambda t. So this one gets the minus dt. Okay, so now we have our definitions. This right here is the Fourier transform. And this right here is the Fourier inversion formula, or is also referred to as the inverse transform. All right, so this gives us a way to go back and forth between physical space, where you have a function of x or t, and frequency space, where you have f hat of lambda. So lambda is a frequency variable. So it's the idea of frequency content of your signal, that's f of x, or if you want to think of it, f t. All right. Now, this looks just like the formula for complex Fourier coefficients, except it's on the entire real number line instead of a bounded interval. Otherwise, it looks exactly the same. Here, instead of having infinite sum, a doubly infinite sum like we did of complex Fourier series, we have another integral from infinity to infinity with no minus in the exponent. So instead of summing over your frequency variable, discrete, you're integrating with respect to your frequency variable as continuous. All right. Now, so when does this formula actually work? So when do we really have f of x equal to all this? Because it seems hard to believe that we'd actually have equality in this case. But we really do, under these circumstances, if f is in C1, so it's continuously differentiable on all the real number line, and the f is absolutely integrable. So take the absolute value of f and integrate that on the entire real number line, then you get a finite value. So certainly f has to go to 0 as your variable, f of t has to go to 0 as t goes to plus or minus infinity for that integral to have a chance of existing. Okay. So under these conditions, we're guaranteed to have this equality. So you can take f, take its Fourier transform, then take the inverse transform, and then you're reconstructing f exactly. Okay. Now, but that's the case where f is continuously differentiable. Now, What about if f has a jump discontinuity? We know what happens with Fourier series. Fourier series converges to the average of the values to jump. And here we have the same thing. So if f has a jump discontinuity, I take the Fourier transform. If I invert it, I won't recover f exactly. I'll recover the average of f of the values on either side of the jump. So that part works exactly the same. Okay. The reason why we have this assumption is just to make sure that this integral is well defined. Because this is an improper integral. Improper integrals can either be convergent or divergent. So if we have this assumption, because the absolute value of this integrand is absolute value of f of t. So if that assumption is satisfied, then this integral is guaranteed to exist. So it's not absolutely necessary, but it is sufficient. Okay. All right. So this converges. If this integral of absolute value of f of t is known to be finite. Okay. I have one note left. And we're not even halfway through class yet. All right. Let's see. Actually, if there's any other tidbits. Okay. What I'll do, I said this out loud, but I want to write it down also. The trouble is, I don't like to write too low on the board because down low, like I can see on my screen, like the writing in this middle range is much easier to read than what's above or below, especially below. It's just terrible. Okay. All right. So. So what we can say is, if there's a jump discontinuity at x, then what we can say is that 1 over square root of 2 pi integral minus infinity to infinity f hat of lambda e to the I lambda x. So this is lambda x dx. So this is the Fourier inversion formula. The result that it gives you is one half f of x plus 0 plus f of x minus 0. So the average of so if this is your behavior at x, so this is f of x minus 0, the value to the left of a jump, and this is f of x plus 0, the value to the right of a jump. Okay, just like Fourier series. Okay. But yeah, which is expected because this reconstructed f of x is expected to be a continuous function. So if the original f is not, then we're doing the best we can. Okay. So, questions about anything? No. Okay, so what I have here are some examples. But when I was writing this, I was kind of lazy. Where we examine some functions and compute the Fourier transform, and what I wrote down here is the final result. So I've probably taken a gamble at seeing if I can actually work out the integral. Maybe that'll chew up the rest of class time, but we'll see what happens. Or I could get lazy again and write the final result. Like, here's what we're supposed to get. is something that is not entirely in the notes. Okay. So, oh, whoops. Okay. So my function is a simple one, but it has a jump discontinuity. So it's equal to 1 if t is in minus pi to pi, and 0 otherwise. So that helps because now we don't have to integrate from minus infinity to infinity. We're integrating over a finite interval. So f hat of lambda, which is defined to be 1 over square root of 2 pi, integral minus infinity to infinity, f of t e to the minus I lambda t dt. This chalk is getting smaller, so maybe I should say when this runs out, class is over. So now, actually, this integral won't be bad. So, because the function is 1 from minus pi to pi, that changes my limits. So 1 over square root of 2 pi, integral from minus pi to pi of this e to the minus I lambda t dt. Now there's two ways I could do this. I could integrate this directly because it's just exponential and that's pretty easy to do. But I want to get to real imaginary parts, work with real value integrals as quickly as possible. So I'm going to write e to the minus I lambda t in terms of its real imaginary parts, cosines and sines. So what we have is cosine of lambda t, and then minus I sine lambda t. And I'm not going to peek ahead. Like, this is really going to get me. Okay. Now, cosine's an even function, sine's an odd function. We're integrating from minus pi to pi, symmetric interval. So the integral of this is 0. So we can forget about it. So now I can write this as 2. So in other words, square root of 2 over pi. So I'm going to put a 2 here, which cancels part of the square root of 2 below. And from 0 to pi, cosine lambda t dt. And that's going to be easy to do. So we'll have square root of 2 over pi sine lambda t over lambda with limits 0 and pi. Okay, so well, at 0 we're going to get 0, so we just go ahead and plug in pi. Now, the thing to keep in mind is, all right, so there's our final results. So those are Fourier coefficients. Now, Fourier coefficients, a Fourier transform generally can be complex. It just happens to be real in this case because it's an even function, which is also true of Fourier series, as you're showing in the last problem of homework 2. Now, we have a problem here if lambda is 0, except we can use the fact that the limit of sine t over t is 1 as t goes to 0, so we can actually get a value for this. Okay. Now, as far as how the function behaves, if we look at the graph, so it's 0, then it jumps up to 1, and back down to 0. Now, a constant function has just one frequency 0, because it's not changing at all. There's no oscillation. Now here, this function is not constant. It's piecewise constant. But for the most part, we expect the frequency constant to be concentrated around 0. And sure enough, as lambda goes to plus or minus infinity, so if these go to 0, as lambda goes to infinity in either direction. But only with decay rate lambda to the minus 1. that's because of discontinuity. The same thing we observed with Fourier series. Okay, now at x equal plus or minus pi, what we have is converges to 1/2. So if we take the Fourier transform and then we take the inversion of that transform, that will converge to 1/2 at the discontinuities, as I stated earlier. Okay. All right. Now, another thing worth pointing out is if I were to take this Fourier transform, so let's look at the reconstructed function, at least as an integral form. So f of x would be 1 over square root of 2 pi, integral minus infinity to infinity. This Fourier coefficient, so square root of 2 over pi sine lambda pi over lambda e to the I lambda x d lambda. Okay, so this integral is a reconstructed function that will be equal to the original signal everywhere except at the jumps where it'll equal 1/2. Now, this again is an improper integral. And I just want to point out that this integral is conditionally convergent. And what I mean by that is the only reason this integral even exists is because we have this sine lambda pi lambda that assumes both positive and negative values. If we took the absolute value of this integrand and tried to evaluate that integral, it would diverge. So, but that's okay. It's not a deal breaker. The Fourier inversion formula is still valid. Okay. So we'd like to have absolutely convergent integrals, meaning you take the absolute value of this and the integral still exists, is finite, but not absolutely necessary. One of those sticky technical points I mentioned in class, and it never comes up in homework, so you can forget about it. Okay. All right, this next one. Oh, okay. From an integration standpoint, this next one's going to be more interesting. I wonder if I'll be able to do it. Okay. I guess it's pretty much determined becoming energy low during the day, but then we're getting into late afternoon, so it's like, okay. Okay. All right, so this one is also piecewise, but instead of a constant function, it's sort of cosine 3t on minus pi to pi and 0 everywhere else. So once again, our infinite integral for a Fourier transform becomes integral and integral, so that's nice. So we'll have f hat of lambda is 1 over square root of pi, integral minus pi to pi, cosine 3t, then e to the minus I lambda t dt. Now cosine is an even function, so only when it's multiplied with a cosine, because of like a real part, will we actually get anything. So now this becomes, like before, square root of 2 over pi, integral 0 to pi of cosine 3t, cosine lambda t dt. So this unfolds using exactly what I did in the last example, where I write this as cosine lambda t minus I sine lambda t. Here we have an odd function, so that part goes away. All that's the same. Okay, but now we have this. Can anyone tell me, based on some homework problems, how do we handle that?
You can use identity.
Which identity?
Orthogonality.
No.
What? Yeah, which trig identity?
Addition.
No, this half equals to sine this plus this divided by.
Not that one, but pretty much. Yeah, it's one of those. Yeah, it is a product to sum formula, and in this case, when you have cosine and cosine, or sine and sine, what your sum will be cosines. If they're mixed, cosine and a sine, your sum will be sines. So, okay, so 2 pi 1/2. So now I have cosine lambda plus 3t plus cosine lambda minus 3. Actually, in front of a book. Oh, okay. I'm going to write the. Wait. Yeah, okay. I'm going to write the 3 first. So 3 plus lambda, and then 3 minus lambda. dt. Okay. So now I can go ahead and integrate these. Okay. And go back to the readable part of a board. So out front condenses into 4 square root of 2 pi again. And I have sine 3 plus lambda t over 3 plus lambda. And then plus sine 3 minus lambda t over 3 minus lambda with limits 0 and pi. Now I plug in 0, I get nothing. So I just go ahead and plug in pi. But also I want to put this over a... there's no trig. I guess there's no trig involved in business applications. Nothing ever oscillates.
How do you do calculus?
You just quick problems that only use polynomials, exponential, and logarithmic functions.
So you say here is a derivative. Go do likewise. Oh, here's an integral.
Yeah.
And do likewise as well.
Pretty much, yeah.
And say there's this awesome thing called the fundamental theorem of calculus that makes it all work together.
Yeah. So, yeah, I mean, we definitely don't prove anything, and so we touch on limits very briefly just to define a derivative, and we never see a Riemann sum.
Oh,
Yeah. It's kind
how
of, it's
can
good.
you live without Riemann sums?
So that's why I don't want to teach this class anymore.
oh, yeah, looking for somebody to take a place.
Yes, please. I did not work for all these years to become a math professor to teach business calculus. Okay. So, all right. So now I plug in pi. What?
Is lambda a whole number or
Lambda can be any real number. So that's why when we plug in pi, we're not going to get 0. Yeah. Otherwise, it'd be kind of a fruitless exercise. So, okay. So while I'm plugging in pi for t, I'm also going to put everything over a common denominator. So my common denominator will be 9 minus lambda squared. So at least that part's in place, because that is in my final expression. So everything else I'm going to do is in the numerator. So I have sine 3 plus lambda pi plus sine 3 minus lambda pi. Here's what I can do. I can do the opposite of a product to sum formula. It is a sum to product formula. So what happens in this case is that'll give me a factor of 2 up top and same denominator. And what I'll get is Okay, so we're going to have sine 3 pi, which is 0, cosine lambda pi, but that whole term is 0, plus cosine 3 pi, which is minus 1. Okay, that part bugs me, but we'll see what happens. Sine lambda pi. Okay. And then for the other term, we're going to have sine 3 pi, which is 0, times, times cosine lambda pi, but that whole term's gone, minus cosine 3 pi. So minus and minus makes a plus. Okay, this is a problem because now I'm going to get sine. That can't be right because that would just make everything 0. Oh, I know why. Sorry, I have to back up a bit. I should be forced to return to NAF 101 because I did not put everything over a common denominator correctly. And you guys didn't stop me. Because I did the denominator correctly, then I have to put these factors upstairs. So 3 minus lambda sine 3 plus lambda t. Yep. Well, I hope you're not still in mode of, oh, professor knows what he's doing, because some of you see me last long enough to know better. So,
well, all of us should have been.
So only you're excused. Okay.
well, all of us should have been at the other side of the classroom long enough to know better.
Plus 3 plus lambda sine 3 minus lambda t. T is pi, so I'll fill that in. Okay. All right. Now, okay, I need to move this. Okay. Now, I can't use a well, probably the best thing to do with the chance of further mistakes is just to use the sine, sum, and difference formulas throughout. Okay, so now it's going to be really messy. So I have 3 minus lambda, and then I have, okay, sine 3 pi, which is 0, so that wipes that whole term out. So I'm going to have cosine of 3 pi, which is minus 1, and then I have sine lambda pi. Okay, so that part's the same as before. Plus 3 plus lambda, and okay, so we have sine, cosine of 3 pi, which is minus 1, and then sine lambda pi. Okay, over 9 minus lambda squared. Okay, now I think everything's going to work out at this point. So what we have here is we have minus sine lambda pi. Well, wait. Minus makes a, okay, there's a minus from here and a minus from a cosine, which gives me a plus. Okay. All right, so now, if I distribute all this, like 3 minus lambda through the minus sine pi t, lambda pi, and the 3 plus lambda through here, all the terms involving 3 are going to cancel out. Because we have minus 3 sine and a plus 3 sine. So I can ignore these. And then the terms involving lambda are going to add together because I have minus makes a plus, and then I have a plus here. So I'm going to get 2 lambda sine lambda pi over square root of 2 pi 9 minus lambda squared. And that is the correct expression for my notes. So it all worked out in the end. Okay. Now, what's interesting about this expression is, so we have peaks, really, at lambda equal to plus or minus 3. Well, really, we have that vertical asymptote. The whole thing's going to blow up. Here we go again. All right. So, yeah, this does not necessarily blow up at lambda equal plus or minus 3. The reason why is, okay, 2. When, what? Yeah, because pi. So what actually happens minus 3? What will we have if we take the limit? Yeah, L'Hopital's rule, which I don't feel like doing. Well, what would happen is if I were to do that, like, so first derivative, I'd have sine again with 1. Okay, that goes away, and then plus cosine, which would be equal to minus 1. And then down below, we'd have, I know it. Oh, that'll still be a finite limit, because now we'll just have minus 2 lambda, which will be non-zero. Okay, so, all right, so we get a number. The point is that it peaks at plus or minus 3, which makes sense, because what is cosine equal to? Cosine 3t is equal to e to the 3it minus e to the minus 3it over 2. So it's 2 frequencies. So those frequencies should be most important here. Now, the reason why we have other frequencies is because it's not always cosine 3t. It's only on that portion, and then it goes down to 0 after that. But that still means, so when we have these windows, like we just defined to be a certain function only on minus pi to pi, or some other finite interval, the frequency content peaks at the same place. It doesn't really destroy that completely. You just have, instead of having abrupt spikes in your Fourier transform, it just goes down to 0 more slowly after that. Okay. So the behavior of Fourier transform, like where it's concentrated, where are its peak values, that gives us an idea of the frequency content of the function. There's another example that's in the notes where it's, instead of cosine 3t, it's sine 3t. You work it out, same approach, and you get similar behavior. We have these peaks at plus or minus 3. So I'm not going to do that third example because after this second example, it's just not interesting. That I think is definitely more interesting. So I need to step outside and get some water real quick. My body's like, you're thirsty now, drink or die. Okay. All right, so let's go ahead and. So here we'll do a function that is actually continuous. Because all these examples had jumped off this continuity yet. All right, so okay, so we won't finish as early as I expected, but hopefully still early before this thing crashes again. So I better hurry up. Okay. So now my function, my f of t is t plus pi on minus pi to 0, and then 0 otherwise. So it's just behave minus pi, and it peaks. Okay. So, okay. This, oops. I had another typo ready. Okay. So because I have with it, this is going to require integration by part. Will be by. It can help me though, because that's this function. So I can just integrate. So from 0 to pi twice, or times 2, and I'm going to have t plus t. So the definition on cosine lambda t dt. So this comes from, so this is my f of t, and this comes from e to the minus I lambda t, but I'm just taking part because that is for some things. So my integral is from minus infinity to infinity. I cut pi to pi immediately because of this. Then I recognize, oh, the function's even, so I only focus on 0 to pi to cut it down even further. Take the real part, cut it down even more. So I don't feel like writing all that. So, okay. So now we got to do integration by parts. Ugh. So u is pi minus t, du is minus dt, dv is cosine lambda t dt, and v is sine lambda t over lambda. Okay, so at least this integration by parts shouldn't be so bad. Well, the u times v part, boundary term, I plug in t equals 0 and pi. Both of you need the uv part. All I need is my u. I have this, and then I have integral from 0 to pi v du. So cancels with a minus from the integration by parts formula. So all that's left is sine t over lambda dt. Okay. So now what I get is, well, 1 over lambda pull out, square root of 2 over pi, and then I have minus cosine lambda t over lambda from, so then I go ahead and I get pi cosine lambda pi all over lambda squared. But I've used my notes. Wow, did it right. First time. So it's a miracle. So worth making here. Notice the decay rate. The top is bounded. Bottom go. So the fraction as a whole goes to 0 at the decay rate order lambda to the minus 2, faster than the decay rate from the other examples. And the reason why is this function is continuous, whereas the other ones were piecewise continuous. So reconstruct transform, because of the rapid decay rate, and we use the integral from minus to your point to get an accurate reconstruction. So just like the more smooth, more rapidly the Fourier transform decays to 0 as lambda goes to plus or minus infinity. Okay, so well, what I may do, so I'll have a 4th page of notes after all, just not taking your time on them today, is now that I have these worked out, because I didn't have these worked out when I wrote these notes, because the book didn't feel like doing it either. So I may put these in here just so one can look at this later and see, oh, here's where it came about. So.
Much appreciated. It's a whole lot nicer than the assumption I think the book says. Oh, this is a 700 level class.
On your head, forget it. That's so not happening. Okay.
Definitely not on my head.
Yeah.
That much.
Well, because now I think about it, because Monday's notes are already written. I haven't done I started next Wednesdays, and those will be the last ones before the midterm. So then I have a week of not having to do notes. So. Okay, so at some point I will backpatch this. Okay, so now that I have a video record of it all. Okay, well before this crashes again, let's just quit.
Okay.